So we've gone through a philosophical perspective on how data from environmental monitoring might be used for science, um, in terms of thinking about how it lends objectivity to our epistemological approaches to understanding the metaphysical and ontological perspectives on reality. Um, but that doesn't really get us where we mainly want to go with science, because science is not just about describing reality, it's about understanding reality. So in order to get from that basic information to understanding, that implies that we want to know something about causality. And I would say that's probably the primary goal of science, is to understand causal relationships in nature. So to get there, to make that leap from data to understanding, we need to apply the scientific method. Not just think about the philosophy of science, but think about how we actually practice performing science. So this is a perspective on the scientific method you've probably seen since the third or fourth grade. You make some observation that results in you having a question. Um, you see a baby crying, and you say, why is that baby crying? Um, and you can form some sort of hypothesis about why the baby's crying and say, well, I think the baby's crying because it's hungry. Then you can design an experiment where you say, okay, well, I'm going to feed the baby and see if it keeps crying or not. And then based on the results of that experiment, you can decide on the validity of your hypothesis to say, well, the baby stopped crying, maybe it was hungry. Or if the baby doesn't stop crying, then you can say, oh, I need an alternative hypothesis, that sort of thing. And then many times when we do experiments, we end up with more questions than we started with, or our hypothesis turns out to be just plain wrong, in which case that leads back to the question again, illustrating how science is really more of a cycle than it is a one-way road. But so that's an easy enough description of science to introduce the concepts of science to somebody. But if you're actually going to practice science, I feel like we need to define this cycle in a little bit more detail. And the reason I like to do this is because I think it makes it a lot easier to clearly communicate science in terms of writing proposals and writing papers, which are two of the major tasks that you'll probably have to do as a graduate student. So I think we need to put a little bit more detail into the scientific method to understand what it's actually like to practice science. And it helps understand the different kinds of reasoning that we use as we go through this process. So first of all, there's a name for the transition from a question to a hypothesis, a name for the type of reasoning that you do from that, and it's called abduction. You might be familiar with terms like induction and deduction. Well, abduction is specifically the form of reasoning you use when you're looking for an explanation for something, or I would say when you're trying to explain causality. It's like, so if you have a question about some pattern that you're seeing in data, your hypothesis is then you saying that, well, I think that this particular causality is at play that's creating that variation that I'm observing. A lot of times we talk about that in terms of an independent variable and a dependent variable. There's an independent variable that is some indicator of what the cause is, and there's a dependent or response variable that is showing patterns that tell us something about how that causality actually affects the world. Okay, so if hypothesis is a statement about causality, then how do you go about making an experiment? Well, a lot of times we skip this step when we're describing the scientific method, but I think it's very important to make the distinction between a prediction and a hypothesis. And the distinction is that a hypothesis is a statement about causality, and a prediction is a statement about what will happen if that causality is true or is in effect. So using the baby example, if our hypothesis is the baby is crying because it's hungry, often very useful to make sure you use the term because in your causal statement. I don't like to use predictive or prescriptive writing methods, but at least the thought exercise, a useful thought exercise is to make sure the word because is in your hypothesis. And the prediction then is, if I give the baby food, then the baby will stop crying. So that's a very specific outcome that is going to be addressed or be able to address your idea that that causality is at play. So hopefully that distinction makes sense. And I think it's very important because if you can communicate the causality and the prediction specifically, then it'll be a very natural step to talk about what your experiment is, because it's almost a no-brainer at that point. If you say, well, if I feed the baby, then the baby will stop crying, you almost intuitively know what the experiment's going to be. And this is true for a lot of different experimental designs. If you take this step by step from hypothesis through prediction, I think you'll find it much more natural to write about your method section and about your experiment, and it'll be immediately clear to people how you can get from this experiment and the interpretations of its results all the way back to your questions with super clear logic. So this is the way that I was trained to think about the scientific method, and I can't tell you how many times it was beaten into my head, the difference between a hypothesis and prediction, and I really do think it's a good exercise. So the avenue of reasoning that we're taking here through this process of experimental design is called deduction. So we're trying to go from the more general understanding of causality to the more specific test of that causality through testing a very specific prediction that we've made based on that causal relationship. And deductive reasoning is the type of reasoning to go from the more general phenomena to a prediction of what the more specific phenomena is. So a lot of times in science, you'll hear it called the hypothetico-deductive process, and I think that's probably not quite correct. Experimental design is most definitely a hypothetico-deductive process, but I would not suggest that all of science is, because scientific papers wouldn't be that interesting if all they were was about deduction. There's more that we want to do with our results, right? We want to interpret our results. So it's not, discussion sections aren't that exciting if all you do is say whether your hypothesis was supported or not. You want to say what that means. What does that mean in the broader sense, like in the general theory of whatever field that you're studying with your paper? So you want to do some sort of meta-analysis to lead to your conclusions, not simply an analysis. And what a meta-analysis means is you want to pull your data together with previous experiences of previous researchers in terms of looking at other papers, to be able to say how your particular experimental results in the larger theory of what you're studying and what broader conclusions that you can make from that work. And that is the process of inductive reasoning, where you're going from the specific back to the general to say, okay, this experiment turned out to either support my disprove my hypothesis, and this is what that means to my field as a whole, based on what's been published in the past in the literature. So there are a couple of extra steps here that don't typically get introduced in the scientific method when you're just trying to describe the basics of scientific logic to a third or a fourth grader, but they're extremely important if you're actually practicing science. I've added a couple of very important ovals to this, that prediction oval and that meta-analysis oval. And I like to do that because it lets me talk a little bit more about how this maps to how we write about science. And this is probably true for both proposals and manuscripts. There's a lot more in common to those than you might think. When you're talking about your introduction section, for example, in a manuscript that you're writing, it's really all about making the motivation for asking a question and how you have come up with some hypotheses and predictions that you want to test. And really, it's the last paragraph of the introduction that typically culminates with some statement about hypothesis and predictions that then leads you to a method section that says something about the experiment and the analysis that you're going to do. In other words, how am I going to go out and observe or manipulate the world? How am I going to measure the response of the world to that manipulation or the variation in the real world relative to my observations? And then how am I going to analyze those data? Like, am I going to do a statistical analysis? Am I going to do some visual analysis? How am I going to take those data and interpret them to come up with some sort of conclusions? The results section then becomes the output of the analysis. And the results section is then the facts. This is where we talk about the incontrovertible truths about the results of our experiment. And you definitely want to try to avoid interpretation in the results section, right? You're starting to mix up things. And it's usually, in Some cases, there are papers that make sense to combine the results in the discussion, but I think when you're in the early stages of writing in a paper, it's always good to at least go through the mental exercise of trying to separate those. And then if it only makes sense in terms of communication of the science, that you just need to put the results in the discussion for the paper to make sense, then you put them together. But I think when you're first writing a paper, you want to keep those things separate. So the discussion then becomes that meta-analysis and the conclusions. Like, how are you taking those interpretations of the results of your experiment and putting them back into the larger context? So it's the discussion section where you really start getting back into the inductive reasoning, where a lot of the rest of the paper was more deductive reasoning. So we all know that the way you write about science is not really the same way about how you execute science. So it's nice to show this in this nice clear-cut loop of logic, but really you end up jumping around all over the place when you're trying to actually execute science. You learn a lot when you conduct your experiment the first time. Sometimes you have to go back to your hypothesis again because you realize you can't really address your hypothesis with that experiment. There's all kinds of reasons that you can make all sorts of jumps in this loop, but I think it's still a useful model to help us think about how we communicate our science. So where is data important here? And where data are important are the facts. Again, and this goes back to objectivity. Like, why is all of this deductive and inductive and abductive reasoning, how can we root it in some sort of defensible conclusions about how causality works? Well, that's what data give us. Data gives us those facts that are hopefully as objective as we can make them and provide the support that we aren't just making all this up.